All right, so unfortunately, I'll be the fourth instructor or third instructor in the last few days. As you know, Dr. Chang is not feeling well, so he can't come to you today. Very good. So essentially, Chapter 10 is of three topics, or essentially two main topics. One is the VSEPR, which discusses the geometry, right? And if you know the geometry of the molecule, you should be able to know its properties. Like, will it be polar? Right? What will be its boiling point? What will be around its melting point, and so on and so forth. So it's important to know what the geometry is. Okay? The second part of the chapter is supposed to be to explain how do we get these shapes. Right? You already went to tetrahedral. How come it's tetrahedral? Right? So we're going to try and relate what they look like in the atomic form and how do they look like in the molecule. All right? So we're going to try and cover all of those as much as I can in 2 hours, because this is your last meeting for the semester, right? So as an outline, we're going to finish our VSEPR. And if I gathered it correctly, we'll start from 5 bonding pairs, right? Because you got as far as 4 with tetrahedral, right? So, and then we're going to go valence bond theory. And this is explaining why you're getting those geometries, as well as molecular orbital theory, or MOT. Okay? So let's start with the VSEPR first, and then finish it, right? Let's look at PCl5. So how do you draw the Lewis structure of PCl5? All right, so if we follow the rule, we go look at all the atoms. How many valence in phosphorus? 5. And chlorine? 7. All right, I'd write to request that let's have one conversation at a time. It's very difficult to compete. There's how many of you and only one of me? Okay. So 7, and how many chlorines do we have? 5. So a total of 35. So what do? You put the central atom, right? Yes. And then put the rest of the surrounding atoms, right? What do I do next? All right, I'm going to put bonds. 1, 2, 3, 4, 5. So how much did I take away? So a total of 40. I took away 10. What do I do with those 30? I'm going to complete the octet of the surrounding atom. So that's chlorine in this case, right? So we're going to go how many? So we're done, right? We used up all the 30 electrons, right? Anything unusual about this structure? What did we say? Octet. Octet should only have 8. I should remind you that phosphorus is one of the exceptions. In fact, if you look at the periodic table, anyone from 3 downwards can have an exception, can have what we call an expanded octet. If that was nitrogen, is that possible? No, because nitrogen is in the second, right? So it cannot have an expanded octet. So if the question says which one is a real molecule, PCl5 or NCl5, you say that's not possible. Yeah? Because as we just say, nitrogen cannot have an expanded octet. Huh?
Why? I understand it's the rule, but why?
Why? What happens when you go down the... Very good. you have more shells as you go down the periodic table, right? Yep. Okay. Now let's draw the geometry for that molecule. Okay. So if I imagine 5 bonding pairs, so 1, 2, 3, 4, 5, they're a little flimsy. But what's the idea? This 5 bonding pair has to be what? Close to each other, as far as possible away from one another, right? That's because of VSEPR theory, electron shell repulsion theory, right? So this has to go farther away from each other so there's no repulsion between each of them. And the best structure for 5, I cannot hold it up like that, is something like this. Okay? Or in the shape, looks like 2 pyramids fused together like this. So there's a 1, 2, 3, 4, 5 corners. Right? To give you a perspective, this is the 5. This is your, remember the tetrahedral? Right? So there's 1, 2, 3, 4. Right? So those are the bases of the different shapes. All right? So for the going back to this, what are the angles then? So the angles are, this guy over here has to be 90 degrees, right? And this one would be 120. Okay? So in fact, you'll have now 2 different bonds. One that are going this way, and another one that's going this way. We refer to that as the eggshell. And so this guys over here would be your equatorial. Okay? Good so far? Right. This one? Equatorial. Right? It's in the, like this, and then here's your eggshell positions. All right? Okay. Let's do exactly what Dr. Foster did. What did she do? When you started with 4, let's try taking away 1 at a time, right? So let's try different molecules relating to that. Let's try the Lewis structure now for SF4.
What is this called, this shape?
This one? Oh, very good. So trigonal bipyramidal. Okay? Bipyramidal. Let's go to bipyramidal, 2 pyramids. SF4. If you follow the same rules we did for PCl5, you should arrive at a structure like this. So in fact, sulfur will have 6, fluorine will have 7 each, times 4. Will be 34. Okay? Do I have the correct structure? What am I missing? So I have an octet here, I have an octet here, and octet here, right? But that accounts only for 32 electrons. There's 2 electrons left. Where do we put the 2 electrons extra? On the central atom. Can sulfur have that extra? Why? It's on the expanded octet. If that was oxygen, it can't be, right? Because oxygen will be on the second, right? Good. So what kind of shape do we have? So do you agree with me that there's 2 ways to make this structure based on this, right? So we can remove a lone pair. Where can I remove a bond? I can remove one from the eggshell position. I'm going to call her that. That's one option, right? All right, I put the lone pair in there. What's another option that's supposed to be different? Can I put it here? It should be the same thing, right? So either one of these two will arrive at the same structure, right? But remember, this is the eggshell position, and there's the equatorial. So there's 2 options. One is to remove it at the eggshell. Another one is to remove it at the equatorial. Okay? You have to suffer through my drawing because I couldn't get the PowerPoint to run. But you can clearly see the 2 options, right? Which one is more stable? Equatorial? Axial? Which one? You don't know. Yeah, that's a good answer. Yeah? So let's count the repulsions. One thing to remember is that if you have repulsion between 2 bonding pairs, is that weaker compared to the repulsion between 2 lone pairs? Which one is much more unstable? All right, I'm going to draw it to you so that you can clearly see. So a bonding pair, here's the electron is slightly distributed like this, right? For a lone pair, how is the electron distributed? It's just on that one atom, right? So if you have 2 of this next to each other and 2 of this next to each other, which one has a higher repulsion? This one, right? Because they're going to be more crowded. Remember, those are all negative. So if you put negatives together, do they like each other? They don't like each other, right? So this is in fact more unstable. And what will be in between? All right, so you can have a combination of those 2 or that other 2. Clear? Let's make a count on these 2 options. I'm going to use the green one when we're talking about this. Okay? How many BPLP at 90 degrees? You sure? Oh, you're going the wrong way. Can you see it? So here's my lone pair, and here's my bonding pair. So that's 1 90 degrees, 2 90 degrees, 3 90 degrees, right? So this one will have 3. You follow? Let me see if I have a diagram. Give me a second. All right, so this is the first structure in green. You can probably see it better with this. Here's my lone pair, and here's my equatorial bonds, right? So how many 90s do I make? 1, 2, 3 90s, right? 3 90s. Let's do the opposites. Let's say I put this one on this one over here. How many 90s? There's only 1, 2. Right? Why am I looking at the 90s, not the 120? Because 90 is closer, right? So if those lone pairs are close to one another, remember, they're going to start repelling each other. If it's a 120, they're farther apart from one another. So I'm counting the 90s because those are the most unstable. So in the first structure, I'm going to end up with 3. That's not good, right? In the second structure, I only ended up with 2. So which one do you think is the preferred structure? This one over here, right? Let me just get this one before I forget. So this is so for the orange, it's 2. For the other structure is 3. All right, so this is more stable. Okay? So this structure is now, what do you call this structure? What do you call that? The seesaw is a more common name, but it's also called distorted tetrahedral. Okay? So it can either be a seesaw or a distorted tetrahedral. Okay? So that's the structure when you have 5, right? And 1 lone pair. Okay? Right? I'm going to do one more and you'll get the idea. How about if there's 2 lone pairs? Okay. Fluid structure for ClF3. Cl has how many valence? 7. Fluorine? 7 times 3, or total of 28. So it goes Cl How many is that? 24. So you have 4 electrons left. Where do you put the 4 electrons? Huh?
You can put one, you can put 2 electrons on top, and put 1 electron on the bottom.
Well, does it really matter if I go this or this? Or this or this? Does it really matter? It's the same thing. All right, as long as you have 2 pairs around, 2 extra pairs around chlorine. Okay? Double bond. We haven't done double bonds yet. Let me just show first this one, okay? So here's the original 5 bonding pairs. Where will I put the lone pairs? Where are my options? I need two, right? So I can go one here and one here, right? Option 1. Another option. Follow? You follow what I did? So in the first one, I took one from the axial and another one from the equatorial, right? In the second one, I took both from the equatorial, right? And the last one, I put the two axial. Okay? All right. Let's do the same accounting as earlier. So how many lone pair at 90 degrees do you have in the first example? I think you need to see it again, huh? So there's one lone pair. Agree? So I'm going to say 1 for this one. How many lone pair, bond pair, 90 degrees? Lone pair, bond pair. So this one. All together. So I got 1, right? 2, 3. Yeah? Yeah, but some people said 2, 5, yeah. I wasn't saying you're wrong. All right? How about the other one? First of all, do we have lone pair at 90? Right? There's no lone pair at 90 because these two are at 120, right? So that's good. And so how many lone pair, bond pair at 90? 1, 2, 3, 4. Agree? So 2 up top, 2 up the bottom. Okay? And how about this? Yes? Lone pair. Lone pair, bond pair. Yes. How about this one? 6. Quickly, right? So which one do you think it is? I'm going to choose the first one. You see this? That's very unfavorable, right? So we're not going to choose this one just because of that. That's eliminated quickly. So the choice is between these two. And obviously, I'm going to go with this. Okay? And what do we call that? Distorted something, right? What do you see? T-shape. Okay? So I hope you get the point of the VSEPR theory, right? See, what I have now is a summary of all of that. So what you'll find in the table, please distribute. Give me back the extras, if you have any. Everybody has one? Pass it to the back. All right, so if you look at the table I just gave you, it gives you a summary of the different shapes. And just to tell you what the designations mean, so if you see this, it's in your first column. This means this is your central atom. And this is your bonding pair. And this is your lone pair. So all you have to do is draw the Lewis structure as we've been doing. And then looking at the central atom, and what characteristics do they have? How many bonding pair? How many lone pair? And to each of those different shapes are the corresponding structures. Okay? So on the last column, you'll see what we will call them. Okay, T-shape, seesaw, and all of that. Right? And you know how we figured out those seesaw structure, right? Okay. I'm not going to go through the 8 because I'm assuming you can follow the same argument, right? Depending on the repulsion, right? Okay. As we said, we needed to know the geometry because we need to figure out whether it's polar or not, right? Let's try the simplest one, BeCl2. If you draw the Lewis structure and the geometry of this, you'll find that it's of this structure. And we say this is linear. Okay. Now there's two levels of polarity. You call it, is it the bond polar? How do you know whether a bond is polar? You look at the electronegativity. As long as there's a difference in electronegativity, that bond will be polar. The next question is, yeah, the bond is polar, but is the molecule polar? Right? So if you look here, there is a polarity here because this is more electronegative, right? So you can draw a dipole moment going that way, right? Because the Cl is more electronegative. But there's also another one going this way. So is the molecule polar? It's a polar bond, but non-polar molecule. That means when is something non-polar? When the when the dipole moments are canceling out.
So if it's like a diatomic element, then it's not polar.
Yes, because it's going to cancel out. So this one would be the one dipole moment going this way, the other one going the opposite direction, same magnitude, opposite direction. What happens to vectors? They get knocked off. They get deleted, right? Another example. What do we call this shape? Trigonal planar, very good. Is this polar? You should have asked me, is it the bond I'm asking about or the molecule? Right? So the bond, the bond is polar, agree? So in fact, this is going to be right? Now it's not quite obvious, but if you do some geometry, you'll see that the resultant of this 2 will be in opposite direction as this. Right? Remember vector resultants? When you have 2 going like this, you get the resultant in the middle. And what happens is that this will cancel out this one. So this one is a non-polar molecule.
But how are we supposed to know?
Well, that's why I'm giving it to you now. So either you do the geometry, or when you see something like this, I'm going to give you a pattern in a little bit. I'm giving you an example first. If you see a structure like this, right, in a trigonal planar structure, those are going to cancel out. Where else do we see this structure? In the trigonal bipyramidal. You're going to see that in a little bit, okay? What? That's a generalization I'm going to give in a little bit, okay? I'm giving you first the slow development of it, okay? How about this molecule? Is it polar? Yeah, bond and molecule. So this is going to be polar bonds, right? Well, what do you notice? This 2 will cancel out. But how about this guy? Right? So there's a remaining dipole, so it will be a polar molecule. Okay? All right? Okay? Remember PCl5? What was the structure of PCl5 again? Is that going to be polar? Bond? The bonds are polar. Very good. Why did we say it's non-polar? This 2 will cancel out, right? And we said, remember we saw this already before? That's also going to cancel out. So this will be a non-polar molecule. Okay? All right, so let's make a summary now. How do we know when something is polar and nonpolar? So obviously, if the bonds are nonpolar, they're not going to be polar, regardless of the geometry, correct?
And it depends on their electronegativity.
Correct. So when I say they're nonpolar because of the bonds, that means their electronegativities are the same. An example would be okay. So those are examples. I want you to draw the Lewis structure and find. We're having that extra conversations again, please. I still have 1 more hour, so. All right. So one would be if the bonds are nonpolar, right? And usually that is when you have the same atom in the molecule, right? Obviously because they will have the same electronegativity, so they will cancel out. Next one. So the second one, that you're sure something is nonpolar if there is no lone pair around it. What was the example? We had the BCl3. We have the BeCl2. There's no lone pair in the central atom, right? And we knew that was going to be nonpolar. PCl5, did we have a lone pair in the central atom? No, so it falls under this category, right? So examples include examples I just gave you earlier. Okay? So the second one, so a molecule is polar when there is a lone pair except for those two types. What are those two types? Why did I single out those two structures? What is AB2E3? Linear, right? And how about the AB4E2? Square planar, so that means there's 4 corners, right? So they always cancel out, okay? Right? And also, if you find different atoms around the central atom, then it's going to be polar. Okay? Let me give you an example. I forgot. So this one, that's going to be polar. An example of this would be HBr. Is HBr polar or not? HBr. Polar. There's only one bond. Since there's only one bond, nothing's going to cancel, so it's going to be polar. Yeah? What is this structure? Remember, PCl5 is nonpolar. But change one of the chlorines, now they're not all the same around the central atom, it becomes polar. Okay? So PCl5 will be nonpolar, but if I change at least one of them, it becomes nonpolar. Polar, yeah, polar. Okay? Any questions so far? So you got VSEPR, right? You're able to determine polarity based on the geometry and the structures, right? Okay. I'll give you a 5-minute break, and then when you come back, we'll try explaining why we get these structures, right? Valence bond and molecular orbital. All right. So there's two premises to the valence bond theory. One, the sharing of electron happens between the overlapping atomic orbitals. I'm going to pinpoint that in a little bit. But that's the key word there, right? So overlapping atomic orbitals. The second part of the definition, it says that when these guys overlap, the energy goes down. It becomes more stable. So the lowering of energy when you start sharing electrons. So those are the key words there, right? So I'm going to show you an example to understand that better. Let's try H2. Right? What's the valence electron of, or valence shell of H2? So H2 will be formed between two hydrogens, agree? Right? Which orbital of hydrogen? The 1s1, right? So the two overlapping orbital is the 1s1 of this guy, and, or I should say just the 1s and the 1s of this one. Okay? All right? So those are the first part of the premise. So you're saying there's overlapping orbitals. For H2, those are these two 1s's. Okay? Now, the other part of the definition is that, okay, I start with these two 1s's, right? And when I form a bond, what happens to these two 1s's? Are they going further away from one another or starting to come together? So they're going to start coming together. So in fact, they come together, closer, and then closer until they form the bond, right? So here's the bond formation. Okay? And so if I plot that in terms of energy, what's going on is, let me use colored. Formation, bond formation. All right. So now if I plot the energy, what did we say? The energy of this is going to start going down, correct? Because as we said, they're trying to form an interaction. So if I plot the energy, the green color, it's going to go like this. Okay? What does that green line mean? So this green line, this part of it, energy goes down as bond is formed, right? And how do you form the bond? You're supposed to be the nuclei of one is going to attract the electron of the other. So there will be at some point where in the happy situation where they form the bond. So this is a good one. So it's going to go down until the lowest point is when you have the bond. Right? What happens now in this area of it? Why is it going up? Why is the energy going up? Everybody follow? So if here's my two 1s's, you agree that at the center of this is a proton. Yeah? And then outside is your electron. So this proton is going to attract this electron. So they're going to form an interaction. And vice versa. This guy, this proton here, will attract this one. So they're going to form a stable interaction, forming a stable bond. What happens now if I keep pushing them together? What happens? The plus and the plus will become too close. And what happens when the plus and the plus become too? They start to repel one another. Right? So this is why this is happening, because they become too close. Right? There's a happy medium where they're all stable, and then when they become too close, the energy just pop back up, because the positive and the positive are now pushing each other away. Good? Right? So you can imagine, so this is what they say. Bonds are formed this way, according to this theory. All right? So we need to, what did we say? We need to identify an overlapping orbital, right? And then there must be an accompanying lowering of energy as the bond is formed, as we illustrated in that drawing. Any question before I proceed? Good? Right? Okay. And if I define some terms, this distance that distance is your bond length, right? So the distance, this defined by this distance is your bond length. And what do you think is this change? What is this? That's the bond length. What do you think this is? Bond. What's the other thing that's associated with bond? Bond length. Bond. Keep going. Oh, close. Energy. Are we good? So now that defines the energy between the bond, and then it defines the bond distance. Good? Huh? Let's try another example. HF. Okay, tell me, so the first thing you need to do is identify what orbital will I use. So H will again contribute its the 1s. How about the F? How am I knowing this? I'm picking the one shell or the one orbital which only has one electron on it. So let's draw the configuration of the valence of fluorine. What do you have? So for fluorine, if I draw the orbital diagram, I'm just going to go to the 2s and the 2p. Right? That's the valence orbital for fluorine. So which one do you think am I going to use for the sharing of electron? The 2p, because this is the one that's only half filled. So it's going to share this one, which only has how many electrons is the 1s? It only has 1, and this has 1, so perfect. We can share those two. So in fact, fluorine will contribute its 2p. All right? So in the same drawing we have earlier, instead of two 1s's, what do we have? We have a 1s of the hydrogen coming close to a 2p. How does a p look like? A dumbbell, right? So they're going to start, this two is going to start to overlap. Okay? So that's what the valence bond theory says. I have to identify what orbital is necessary, the one that's half filled, and I'm going to make those two overlap. Okay? All right. Let's do H2O. So once again, hydrogen will contribute the 1s's, and you have two hydrogens, so there's two 1s's, right? How about oxygen? So if I draw the valence of oxygen, how does it look like? Okay? So I'm going to use this one and this one. This one overlapping with one of the 1s, and then this one overlapping with the other 1s. Okay? So if I draw this, here's my 1s, and here's my 2p from oxygen. One's going to go this way. Right? Can they both go up? How are the p orbitals situated? Each one along each axis, right? So if one of them is going this way, the other has to go on another axis, right? So those are the two p's. So where do you think the 1s were going to go? One of the 1s will go here, and the other 1s will go one here. And that's supposed to be the overlap for H2O. But what's the problem? Do you have a problem with that? They're too close. What was the angle again for H2O? For tetrahedral? Was it 90? 109.5. So if I follow this, this tells me this has to be 90, right? But this is not true. Because what we know is that the angle has to be 109.5 degrees. Aha. So how do you think the valence bond theory tries to explain that? Everybody with me? So if the angles were 90, I'm done, right? I've explained it already. But since the real observed angle is 109 or close to that, I really have not explained it yet. So to explain this, they invoke what they call hybridization. So another one here is uses it uses hybridization. And in simple terms, this only means mixing of orbitals. Okay? So let's look again at oxygen. So we know it has the 2s, the 2p. And we know it's going to go like this. Okay? And we said if we keep it that way, we can't explain the angles, right? So hybridization invoked that this orbital has to mix. So what do I mean by mix? So they're going to mix this. So what happens when you mix them? Put an onion in and some tomato, what comes out? Soup. No? Oh, nobody got the joke. Okay, all right. Whatever. So you mix an S with the P's, what comes out actually is what they call an sp3 hybrid orbital. And it's easy to follow. How did I know it was called sp3? Because I used one of the s's and 3 of the p orbitals. Okay? So that's why we call it an sp3. And they say that when they do this hybrid, right, they look like this. Here you go. I'm getting stuck with my drawing. So each of this, what I'm trying to draw here, is that this will end up to be 109.5 degrees. I just can't draw it very well, right? But it's 109.5 degrees. Okay? And that's what we expected for water, correct? What if I have a double bond? So far I've shown you what single bond looks like. So single bonds are head-on overlapped. What we mean by head-on is what we just did. The two orbitals coming together head-on. Okay? And this is referred to also as a, so head-on overlap is also called a sigma bond. Okay? Now double bonds contain one head-on and one side-on. Okay? Again, head-on is something like this. Right? So that's a head-on overlap. Side-on overlap would be something like this. One p orbital overlapping with another p orbital such a way. So that's why it's called side-on, because the overlap is right here. Okay? And this is referred to as, if this is a sigma bond, this is referred to as a pi bond. Okay? Right? Okay. Let's draw it for this molecule. Aha. So again, once again, how many sigma bonds do I have in this structure? I have a sigma here, yes? I have a sigma here, because remember, all single bonds are sigma. And how about my double bond? It's a sigma and a pi. So one of this would be a sigma. I was going to go there. So what about a triple bond? That was my question. Good guess, but it's the other way around. 1 sigma and 2 pi, right? For the triple bond, it's 1 sigma and 2 pi's. Okay? Right. So let's draw the structure for this one. It'll be funky. All right. So a few things about hybridization. So the number of hybrid orbitals is determined as the number of sigma plus the number of lone pair. Let's try out that one carbon. What's the hybridization on that carbon? How many sigmas do I have? Around this guy, I got 1, 2, 3. Okay? And here's what you do. You go 3. You mentioned S first. And what follows S? P. So SPP or SP2. You follow? So just look at the sigma, right? I'm pointing to that one first. So it's usually have to go by atom. So this one will have a hybridization. This one will have its own hybridization. So in fact, this one will have, as we said, sp2 because it has 1, 2, 3 sigma, so sp2.
So in compound atoms, you can have multiple hybridizations.
Correct. Correct. So let's try this one. What's the hybridization on that carbon? There's 4 sigma, so it's going to be S, P, 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 sp3. Not too bad, right? Another one. Let me continue that thought. And you've seen this guy earlier. What's the hybridization of P? How many sigmas first? 5, right? So an S, 3 P's. And what follows after S? A D. So the hybridization is sp3D. Not too bad, right? Just don't mess up your fingers, okay? So count the sigma on your fingers, including the lone pair, and then you say sp3d. Let me give you another example. No, we're not going to go there until D only. What's the question over there? Let's answer it.
No, I was just asking because I didn't understand. When you're talking about the number of sigmas plus lone pairs, but that carbon, there are no lone pairs.
Yeah, so 0 lone pair. So that's why we ended up with 3. 1, 2, 3. So S, 1, 2. So S, 3. Yeah? Yeah. I got an example for you actually. Look at this guy. So how many sigmas do I have? How many hybrid orbitals do I need for this one? Okay, so total of 4. So what's my hybridization? sp3. It's counted as a hybrid. So the lone pair and the sigma are counted as hybrid orbitals. Okay, so now I have 1, 2, 3, 4. So it's sp3 hybridization. Good? Not too bad, right? Not too bad. Okay. Let me go back to that example over there. And let's draw the orbitals, how they look like, okay? Okay. I'm pretty sure I'm not going to finish all of this, but I'm going to try as much as I can, okay? So what orbital would the HS use? The 1s's, yes. And the carbon?
Oh, the same example.
Yeah, on that example over there. 2? 2? Or 3? How many hybrid orbitals do I have? 3, right? Right? Yeah. Right? There's 3 sp2s. So if you remember from there, how many sigmas do we have? 3. So we need 3 hybrid orbitals. Each one of them would be an sp2. Right? So there's, in fact, they're going to look like this. What was the question again? All right, again, so you count the number of sigma. If you end up in that case, you had 3. So to fill those 3, you count first, the first is S, because that's the lowest energy. So S, and then how many more do I need? 2 more, so that's why sp2. In the other one, I erased it. Oh, over there, in the CH4, how many sigmas are in there? 4. So I got an S and 3 P's. That's how I get it. Okay? Right, so this one is 3sp. This is connected to that guy. Yeah? So this is just this guy. That structure over there. All right. So if I draw the carbon, here's my 1sp, here's my other sp, and here's my other sp. So these are all sp2. Right? And those are corresponding to your sigma position. So what do you think overlaps on this guy? What will overlap with this? Yes? And over here? The other one is, right? How about this guy? The same. Is it an H? No, it's the other. Remember, there's another carbon on the other side. So this guy will also have this, this, and this. So this one will be the 1s, and then this 2 will form the other head-on. So sp2. Okay? Let me draw the orbitals again of this carbon. All right, so let's look at the carbon first. So the carbon, the valence of it will be something like this. Agree? 2s first, and then the 1 for each p. But how many bonds did it make? Total bonds.
Throughout the whole structure?
On the carbon.
4 bonds.
4 bonds. So let me ask you then, how many half-filled orbitals do I need? Hmm? 2? We said we made 4 bonds. So how many half-filled orbitals do I need? 4. Because remember, each one of them will need to have a bond. So each one of them will have at least 1. Right? So in fact, this is not good enough, right? Because it has 1. So this one as drawn can only make 2 bonds. Agree? Because this one can only be shared, this can be shared, but this one is even empty. So the first thing that happens is that they try to equally share the electrons. So how many bonds can this make now? 1, 2, 3, 4. How many do I need for the hybrid? Yeah, how many should I include in the hybrid? You know it. It says sp2, right? So it says S and then the 2 p's. So this will hybridize, right? sp2. So we have to hybridize those 3. Okay? And what will result from this? Okay? So each one of them will have 1 each. Okay? Did I lose you somewhere? Let me repeat. So this is what you will get if you just look at the periodic table. Agree?
Yes.
Right? But we said if this is the case, I can only make 2 bonds because there's only 2 half-filled orbitals. So the first thing that has to happen is that I should create 4 half-filled orbitals. So one thing is this going to move to that one on the end. So now I ended up 1, 2, 3, 4, matching the number of bonds that I need. Okay? And then you say, how many are included in the hybrid? The answer to that is how many were sigma? Huh? How many sigma? 3. So that's why I said I'm going to only need 1, 2, 3 to make the hybrid. Yeah? So then it will end up with sp2, 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 and 1p. And as we already said, this will form what do you think this will form? The pi bond. And in this drawing, the pi bond is okay? So we basically are able to account for the geometry and structure of that molecule according to the valence bond theory. Okay? Are we good? Let me just see if you get the point. Let's try PCl5. How do you picture the PCl5 bond? If you look at the phosphorus, what do you have? Yeah? Is this what you have for phosphorus? If you just look at the periodic table? Yeah? Can that account for my PCl5? Can that account for my PCl5? Do you have enough orbitals? So if I draw it this way, how many bonds can I make? I can only make 3. But how many did we make? 5. So how do we make 5? Because remember, what's the hybridization now? S, P, D. So that means I'm going to borrow one of the D. Okay? And the first thing I'm going to do is going to split them apart. So I have 5 okay. How many do I need for hybridization? All 5 of them, right? Because I have 5 sigma bonds. So the hybridization will include all 5 of them. So I'm going to form, what did I form? Good? Yeah? Well, I think I need to give an example with the lone pair. One more example, short one, water. So for water, how many lone pairs do I have? 2, right? So that means, so if we need to make a bond, we need a half-filled orbital. If we need to make a lone pair, what do we need? A full orbital, right? So in fact, this one will signify, so in fact, this will be your lone pairs, and this will be your two sigma bonds. And how many did I include for the hybridization? So I needed one for the lone pair and for the sigmas. So that means I'm going to use all of them. So it's going to be okay. So unfortunately, you're going to miss the section on molecular orbital. Who's taking organic? Okay. You will have to see it again when you get to organic. But I think what Dr. Chang is going to do at the start of the semester, he's going to send you guys an email and try to see if you can get you together so he can discuss the last section of the chapter. Just if you're, especially if you're thinking of taking organic, you really need to hear it, okay? Because that's going to be taken over in organic again. Not much in Gen Chem 2, but more in organic chemistry. Okay. All right. So if you have any questions, just come by the office. My office is in 3F01 next to Dr. Chang's. If you have any question at all,